All right, y'all. Today we're going to be talking about graphing linear functions. Now, when graphing linear functions, we want them to be in y equals mx plus b or our slope-intercept form. And we're going to use two pieces of that slope-intercept form to graph. We're going to use the y-intercept and we're going to use the slope, which is why it's so important to get it into slope-intercept, because slope-intercept has slope and that intercept already written for us. Okay, so let's look at our first example, y equals 2x plus 3. And so the first thing we always want to check when we are graphing a linear function is we want to check to make sure that it is in that slope-intercept form. So a reminder, it is that y equals mx plus b. And this one is in slope-intercept form, y equals 2, which is our slope, x plus 3, which is our slope-intercept. So we are good to go. So before we can do anything else, it's not even really a graphing step. It's more of a I have to have it to be able to graph step. We want to make sure it's in y equals mx plus b. So if it's in y equals mx plus b, then we're going to go ahead and head to step 1. And step 1 is always going to be identify our y-intercept, which is, of course, our b value. And then once we identify that y-intercept, we're going to plot on our graph at the y-axis. So let's look at our function. We have y equals 2x plus 3. B is our y-intercept, so in this case, our b value is that positive 3, which means our y-intercept is, of course, 0, 3. I'm going to go ahead and add that onto my graph. So right here at 3 on the y-axis, I'm going to make a point. Okay, so that's our first step. Plot that y-intercept. Second step is to identify our slope. Which, of course, in our slope-intercept equation, slope is our m value. And then we're going to use our slope as that rise over run value to plot more points. So my slope in the case of my equation is this number right in front of my x. Remember, it's not 2x, it's just that 2. So our slope is equal to 2. And if you recall, when we were talking about slope, whenever we want to represent slope, we want to represent it as rise over run. So if we do have a whole number for slope, we want to go ahead and rewrite that whole number as that number divided by 1. So we are going to rise by 2 and we're going to run by 1. Okay, so up by 2 and over by 1. And just a reminder that I do have that original point of 0, 3, our y-intercept. And then from that y-intercept, okay, I'm going to rise by that change in y value, by that top value. So I'm going to go up by 2. So 1, 2. And then for graphing, we always want to run to the right. That's going to make sure that we correctly graph positive slopes and negative slopes. Our rise will change. We'll either rise up for a positive slope or rise down for a negative slope. But our run, we are always going to run to the right. So I'm going to run by 1. So rise by 2, run by 1. And right there where my little movements end is going to be my next point. And if I wanted to, I could continue and repeat that slope to get some more points if I wanted to. So up 2 and over 1 again would give me another point. Up 2 over 1, another point. Okay, and then once you kind of have the idea of the pattern, you can actually do the same thing in reverse. So in this case, down 2 and to the left by 1, down 2 and the left by 1, and it's just going to repeat that pattern all the way through. And we have a nice good set of points to be able to use for our step 3. So once we have all of our points, our step 3 is to connect our points. With a line and add our arrows to the end because we want it to denote that this line does continue. It is continuous. It's going to keep going on forever. So those same points that I had before, starting with 0, 3, and then that first slope point that I found up to over 1. And then I want to go ahead and draw that nice straight line. And then last but not least, we're going to add our arrows onto the end. To note that this line, we're only graphing the portion that's fitting on our graph, but it does continue forever in both directions. Okay, so graphing linear equations, y'all, is pretty straightforward. You plot the y-intercept, then we use our slope to plot additional points, and then we connect those points once we feel comfortable with a nice straight line, adding arrows to the end to denote that our linear function is continuous. So let's look at another example. Example 2, we have y is equal to negative 2x plus 7. First thing we always want to check, is that in slope-intercept form? This one is y equals mx plus b. So we're going to go ahead and give that one a check. Then we want to identify our slope. Our slope is always that number there in front, negative 2x plus 7. So slope is equal to negative 2, or as rise over run, negative 2 over 1. Okay, then we want to identify our y-intercept. So in this case, it is that b term, so that plus 7, which means our y-intercept is, of course, 0, 7. Okay, and then I'm going to do my 3 steps. So step 1 is plot the y-intercept. So I'm going to plot the y-intercept of 7. Then my second step is to use my slope as rise over run to plot more points. So negative 2 over 1, I'm going to go down by 2 and over by 1. Remember, I always go to the right. And keeping in mind that our slope is negative, that looks like it is going to get us a decreasing line for that decreasing slope. And then, of course, I can repeat that if I want to get more points. So down 2 over 1, down 2 over 1. And then, of course, if I wanted to go in the other direction, left 2 and left 1 and up 2 to get some more points. And then once I have those points, step 3, connect our points with a line and add my arrows. So I'll connect my points through and add my arrows onto the end for that continuity. All right, y'all. I feel like we probably already have the hang of this. So if you would like to go ahead and try example 3 and 4 on your own, go ahead and pause me. And you can do example 3 and 4. And then after you finish, unpause, and I'll go over example 3 and 4 to make sure we're all on the same page. All right, y'all, making sure we're on the same page with example 3 and 4. So for example 3, we have y equals 3/2 x plus 1. That one is in y equals mx plus b form. So we are good to go. Our slope in this case is 3/2, that number in front of x. And our y-intercept is plus 1, so positive 1, or 0, 1, that number that is after our x term by itself, not with a variable. So first and foremost, we want to plot our y-intercept, which is 0, 1. Then we want to use our slope rising 3 and running by 2 to get more points, and that does give us a positive sloping linear function or an increasing function once we connect those dots and add our arrows for continuity. Then on example 4, once again, y equals negative 3x minus 3. That is in slope-intercept form, so we are good to go. Identifying our slope, it is that negative 3, the number in front of x, and we can rewrite that in rise over run as negative 3 over 1. And then our y-intercept is that negative 3 at the end, so a little strange that they're the same, but that happens sometimes, which is, of course, going to give us the y-intercept of 0, negative 3, because it's that number that's not with the x, it's just by itself. So plotting that point of negative 3 right here on our graph first. Then from that point negative 3, we go down by 3 and to the right by 1. And then, of course, we can do the opposite to go in the other direction. So we can see negative slope. It does give us that decreasing shape in our line. And we are all good to go. Okay, so on the back, we're going to talk about some special cases real quick. So let's look at one like example 6. So right off the bat, first thing we might notice is that this is not in slope-intercept form, y equals mx plus b. We have y equals, but we don't have any x. It's kind of like we only have our y-intercept. Okay, so let's go ahead and treat it as that. So y-intercept of negative 4, which of course would give us 0, negative 4 as a point. So let's go ahead and put a point here at negative 4. Okay, and if you notice, there's no slope, there's no number in front of x, okay? And it's just saying y is equal to negative 4. So if y is equal to negative 4, then that means y can never equal any other value. So no matter what x is, y always has to equal negative 4. Now, the only way I could draw a graph where the y value is always going to be negative 4 is if I draw a line straight through that negative 4, so that y is always that value of negative 4 no matter what x is. Okay, now we talked about this when we talked about slope. That is a horizontal line which is perfectly flat, which if you are on perfectly flat ground and someone asked you what the slope is of that ground or how sloped this ground is, you'd be like, it's not sloped at all, which is why we consider this to be a slope of 0. So anytime you have a linear function that is just y equals a number, then that is going to be a perfectly horizontal line through that y value, and it will have a slope of 0. Okay, now checking on example 7, this one is similar but a little different. This time it is just x equals 6. So we don't have a slope value because it's not a number in front of x, it's x equals that number. And we don't have a y-intercept. We don't have a b value, we don't know what y equals. So we actually don't even have a y-intercept. What we are going to have in this case is what we call an x-intercept. And that x-intercept would, of course, be equal to this x value. So our x-intercept is 6, which would give us an x-intercept of 6, 0. So let's go ahead and graph that x-intercept of 6, 0. It's a little different, okay? And then just like how on example 6, we needed to graph a function that was always a y value of negative 4, we need to graph a function that is always an x value of 6. And the only way that we can have a function that is always an x value of 6 is if we drew a perfectly vertical line through that point 6 on the x-axis. And while our horizontal line, it was perfectly flat, we say that it has a slope of 0 because there's no slope to it. This is like the most sloped line ever, so sloped that you almost couldn't really fathom it. It's like a straight vertical wall. And so we actually say this slope is undefined. And we can write that as undefined, or another way you might see it referred to as undefined is that 0 with a diagonal slash through it, which does mean undefined. And just kind of as an extra caveat, we talked about function, not a function. Would this graph be a function? It would not be, because if we did our vertical line test, it's a perfectly vertical line. So if my vertical line moved across it, it would be touching all of the points at once. So this x equals 6 is not actually a function, which coincides with why it has an undefined slope. It's really like a function or a graph that doesn't really make any sense or doesn't work with anything that we can actually compare values to. Okay, but it does still pop up. We still want to be able to identify it and talk about it when it does. Okay, so to finish up, kind of a capper on today, we're going to bring in some of those key features of linear functions. And we've talked about kind of all of these throughout these notes already. And these should be familiar and kind of a review of what we did at the beginning of the year in Unit 1 with functions. So let's go ahead and graph our function first. So of course we have y is equal to 1/3 x minus 3. That is already in slope-intercept form. So since it is already in slope-intercept form, we can go ahead and identify those two important pieces, which is our slope of 1/3 and our y-intercept of -3. So just like before, step 1, our y-intercept of -3. And then we're going to do our slope of 1/3. So we are going to rise, wrong direction. We are going to rise by 1 and run by 3 to get that second point. And then, of course, I can repeat that pattern up 1/3, up 1/3, and vice versa in the other direction. And so from there, I can go ahead and add in my nice line and my arrows on the end. Okay, so let's fill out a few pieces of information from here. So let's go ahead and complete a table of values to match up. So when x is equal to 0, my y value is -3. That matches up with our y-intercept. Okay, when x is equal to -3, our y value is -4. When x is equal to -6, our y value is -5. Going in the other direction, when x is equal to 3, our y value is -2. At x is equal to 6, our y value is -1. And at x is equal to 0, our y value is, when x equals 9, our y value is 0. So something I do just want to show real quick, make sure this table of values makes sense. Our y values are changing by +1. Our x values are changing by +3. So our rise over run would be 1/3. So that does match up with the slope that we have in our original equation. So everything's looking good so far. Okay, so the first two key features we want to talk about are x-intercept and our y-intercept. Now our y-intercept, we've already done that a lot today. That's going to be our 0, -3, because we get that from our b value. We can also clearly see it on our graph. Our x-intercept, we haven't really talked about it today, but it's also pretty simple to see. Our x-intercept is going to come from where our graph crosses the x-axis. It crosses the x-axis right here at 9, so it would be 9, 0. And remember the big difference between x-intercept and a y-intercept. An x-intercept is number then 0. A y-intercept is 0 then a number. Then our slope, we've also talked about that one before today. It's that m value, or in this case, 1/3. And then we've talked about domain and range before. We just haven't talked about it today. But remember, domain and range is domain going to the left and to the right, and range going up and down. So our domain, we talked about this at the beginning of the year, but when we have these arrows, that means we're going to continue on. We're going to head all the way out towards infinity. And I'm going to go ahead and split these because they are diagonal into the two directions that they represent. Okay? And so looking at our domain, to the left, we have an arrow that's going to continue to infinity. To the right, we have an arrow that's going to continue to infinity. So we're going to start our domain the same way we always do when we have a continuous function, which is our x value in the middle, and then our less than signs on both sides. And to the left, we're going out towards infinity, but in the negative direction, so negative infinity. To the right, we're going out towards infinity, but in the positive direction, so positive infinity. So our domain, negative infinity to infinity, and we don't want to change these less than signs to less than or equal to because we can never equal infinity. So we're going to keep those just like that. Okay. Likewise for our range, it's a continuous function, so I'm going to start my range the same way, but with a y in the middle of my two less than signs. Looking at my arrow going down means I'm going to go down towards negative infinity. My arrow going up means I'm going to go up towards positive infinity. And then once again, I can't equal negative or positive infinity, so I'm going to keep it as just less than signs. So linear functions have a domain of negative infinity to infinity and a range of negative infinity to infinity. That's never going to change. So even though for all of our linear functions, they'll have different x and y intercepts and they'll have different slopes, their domain and range is always going to be negative infinity to positive infinity. And there's one other way we talked about saying or stating both of these, and that's anytime we have a domain or range of negative infinity to infinity, we can also state it as all real numbers. So anytime we have that negative infinity to infinity, we can also state it as all real numbers. Just means the exact same thing. Now, the last key feature that we've talked about before is increasing or decreasing. And we've kind of coincided this a bit with slope, but let's just make sure we're all on the same page. So as I go left to right, that's what I think about with increasing and decreasing. From left to right, my linear function does go up in value, which means it is increasing. Which our slope value should always tell us if we are increasing or decreasing. Our slope is a positive 1/3, so that means we are going to increase. A negative slope means decrease. A positive slope means increase. Don't get a negative versus like a fraction or decimal confused. A fraction or decimal doesn't necessarily mean we're going down. If it's a positive fraction or decimal, we're still going to be increasing in value, although just not as fast as if it was a whole number that was also positive. All right, y'all, and that's all it takes to graph linear functions. If you have any other questions, make sure to ask.